Okay, so good day class. Our lesson for today is about Fourier series. So when a French mathematician, Joseph Fourier, was trying to solve a problem in heat conduction, so you need to express a function f as a infinite series of sine and cosine functions. So as shown in this given equation, so f of x equals to a sub naught plus the summation of a sub n cosine nx plus the b sub n sine nx, where n here starts from 1 to infinity. So we can expand this given equation as in this form. So of course, a sub naught is a constant. If the n value here is 1, we can generate these two terms, a sub 1 cosine x and b sub 1 sine x. No? If n is equals to 2, we can generate these two terms, a sub 2 cosine 2x, okay, plus b sub 2 sine 2x, and so on. Okay. So the series generated in equation 1 from the previous slide is considered as a trigonometric series or the Fourier series. And it turns out that expressing a function as a Fourier series is sometimes more advantageous, no, than expanding it as a power series. So in particular, astronomical phenomena are usually periodic, as in heartbeats, tides, vibrating strings. So it makes sense to express uh, them in terms of the periodic functions, okay, like the behavior of sine and cosine function. So we start by assuming that the trigonometric series, okay, converges and has a continuous function f of x as its sum on the interval from negative pi to pi, that is given in this equation 2, no? So we have here the domain x, okay, from negative pi to pi. So our aim here is to find formulas for the coefficient a sub n, this one, and b sub n in terms of the function f. So recall that for the power series, so f of x equals to the summation of c sub n times x minus a raised to n. So we found the formula for the coefficients, okay, in terms of the derivatives. So c sub n is equals to f of n of a over n factorial. Now for this case, in the Fourier series, we have to use integrals. Now if we both integrate, okay, yung equation 2 and assume that it's permissible to integrate the series term by term, then you can obtain this equation. No? So simply from the previous equation, equation 2, we integrate both sides from negative pi to pi. So we can generate this, okay? So starting with the first term here, of course, if we try to integrate from negative pi to pi, so given is a sub naught, no? So a sub naught here is a constant, so we can actually factor it out. Negative pi to pi t sub x. Okay, so this will give us a sub naught times x evaluated from negative pi to pi, no? So upper limit minus the lower limit, this will give us pi minus negative pi. So of course, if you try to simplify, this give us pi. Negative times negative is positive, so pi plus pi is 2 pi. No? So this give us 2 pi times a sub naught. Okay, so plus, of course, we can distribute the integral here from negative pi to pi for the two terms. Clear the drawing. Okay, starting with this a sub n. So we can use this space. So from negative pi to pi, so cosine n x dx. Okay, so we factor out the constant, which is a sub n. No? So here we can let the variable u to represent nx such that du is n dx. So on dx natin is 1 over n du. So we're gonna replace this by or as u. Okay, dx is 1 over n du. So after that, can rewrite this as in this form du, no? Okay, so we're integrating in terms of variable u, so we can factor out 1 over n cosine u du. Okay, so recall the integral of cosine u is sine u. Okay, so here 1 over n, okay, sine u evaluated from negative pi to pi. So simplify 1 over n. What is u? And x evaluated from negative pi to pi. So upper limit minus the lower limit. This will give us n pi minus sine negative n pi. Okay. So if we try to evaluate this sine n pi, this is always equals to 0. Kasi ni unit circle for if n is equals to 1, this will give us sine pi, no? Okay, if n is equals to 2, this will give us sine 2 pi, which is always equal to 0. So similarly, if we try to evaluate sine negative pi, uh, recall that the sine of negative x is negative sine x. Okay, so if sine n pi is 0 times negative, it is always equal to 0. So the result here is 0. Okay, now for the last term, okay, so the integral of the b sub n sine nx dx. So we can factor out the constant, which is the b sub n. So we're left here with sine nx dx. Okay. So negative pi to pi sine u. Okay. Again, dx is 1 over n du. So negative pi to pi 1 over n sine u du. So again, we're integrating in terms of this variable u, so we can factor out 1 over n. Sine u du. So what's the integral of sine u? This is equivalent to negative cosine u, no? So this will give us negative. We can factor out the negative sign. Then cosine u evaluated from negative pi to pi. So 1 over n. So what is u again? Nx. Then minus cosine negative nx, no? Okay, so cosine nx, if we try to evaluate that, so if we have two possible values now, it's either negative 1 or 1. Because if 10 is equals to 1, we're evaluating, so actually this is pi, no? Okay. Kasi upper limit minus the lower limit. Kasi from here, this is negative 1 over n cosine nx, diba? So nx evaluated from negative pi to pi. Okay, so upper limit in terms of x minus the lower limit. So if n is equals to 1, so we're evaluating cosine of pi. What is cosine of pi? Cosine of 180 is negative 1. Tama? If n is equals to 2, cosine 2 pi. So cosine 2 pi is 1. No? Then for this term, so recall natin, cosine of negative x is always positive x. So we can rewrite this expression as in this form. No? So n pi, then negative cosine negative n pi. So cosine of negative n pi is positive cosine n pi. No? So negative. So whatever value of cosine n pi will simply negate by this negative cosine n pi. So this will give us a, of course, a zero value. Okay, so let's check our answer. So the for the second term, the result is zero. Okay. So because n is an integer, similarly, if we try to evaluate the last term, this will give us a zero value now. So from this equation, so we're left here with this expression along our equation. So the integral of negative f of x dx from negative pi to pi is equivalent to, okay, so this term lang yung first term, 2 pi a sub naught. Okay, so of course, by dividing both sides by 2 pi, this will give us the formula for a sub naught. So, ang a sub naught natin is clear drawing. Okay, 1 over 2 pi times the integral of f of x dx from negative pi to pi. Okay, now to determine yung next coefficient or constant a sub n, so for n greater than or equal to 1, we this time we multiply both sides the equation 2, okay, by cosine mx, where m here is an integer, and again, if you try to represent that, m should be greater than or equal to 1, no? And integrate term by term from negative pi to pi. So we can generate this equation, okay? So if we try to, of course, distribute cosine mx dx, this will give us this expression. So if we try to evaluate uh, this last term, okay, this will give us a zero value for all n and m. And if we try to evaluate this cosine nx cosine mx dx, so this give us the two possible values, so it's either 0 or pi. So 0 for n not equal to m, and pi for n equal to m. So from this equation, okay, so we can equate this to this one, yung second term natin. So possible value niya would be pi, okay, times a sub n. Okay, so of course we simply divide both sides by pi. This will give us a formula for a sub n. Okay, and for the first term, we already evaluate this. So this turns out, of course, to be equal 0, no? Yung the integral of cosine mx dx from negative pi to pi. So this is similar to the integral of cosine nx dx, okay, that we evaluated from the previous slide. So yung formula natin for a sub n is 1 over pi times the integral of fx cosine nx dx, okay, from negative pi to pi. Similarly, we can multiply both sides the equation 2, this time by sine mx, no, and integrate from negative pi to pi, then we can obtain the formula for b sub n. So 1 over pi times the integral of fx sine x dx from negative pi to pi. So definition, so let f be a piecewise continuous function on negative pi to pi, then the Fourier series of f is a series in this form, where the coefficients a sub n, b sub n is this series as defined by the following formulas for a sub not a sub n and b sub n, no? And they're called the Fourier series or coefficients of the given function f. So example, so find the Fourier coefficient and Fourier series of the square wave function f defined by this given function. So f of x is either 0 or 1. Oh. So 0 given the domain from negative pi to 0, and this is 1 if the domain is from 0 to pi. No? And we also given here the periodic value of our function as 2 pi. Okay, so f of x plus 2 pi is equals to f of x. So if f is periodic with a period of 2 pi, and we can graph the given function as shown in figure 1, is similar to this one. Oh. So from negative pi to 0, the value of the function is 0, no? Okay, and this is 1 if our x is from 0 to pi. So this represent yung one cycle, okay, or one period cycle, okay, from negative pi to pi. So just take the absolute value. This will give us a value of 2 pi. Okay, so since this is pi, this is also pi. So add this 2, this will give us the periodic value as 2 pi. So using the formulas for the Fourier coefficients, okay. So recall this formula for a sub naught. So our function is defined as piecewise, diba? Either 0 or 1. So 0 siya if our domain is from negative pi to 0, and 1 siya kapag from 0 to pi, right? Okay, as shown in this given. Okay, so of course 1 over 2 pi is a constant value, so we can distribute this to these two terms. Okay, so of course if we try to evaluate this will give us of course a zero value. This one, this will give us of course this will give us what, so 1 over 2 pi, so the integral from 0 to pi dx. So this is 1 over 2 pi, so x, okay, evaluate from 0 to pi. So 1 over 2 pi, of course, this will give us pi minus 0. Okay, so pi minus 0 is pi times 1 over 2 pi. This give us a 1/2 value. Okay, so of course for n greater than or equal to 1. Now for the second coefficient, e sub n, so recall this formula. So 1 over pi. So again, our function is piecewise. So from negative pi to 0, the value of our function is 0. Then, of course, times cosine nx to give us a 0 value. Okay, that's why we have here 0 dx. Then plus, of course, 1 over pi. Then times the integral from 0 to pi. Okay, the value of f of x from 0 to pi is 1. Then times cosine nx is cosine nx dx. So of course, the first term here is of course 0. Okay, so we're evaluating here cosine nx na lang dx from 0 to pi. So if we try to evaluate that, so 1 over pi from 0 to pi cosine. So we can let the variable u to represent nx such that du is n dx. So ang dx natin is 1 over n du. So cosine u, then 1 over n du. So 1 over pi, we can factor out 1 over n. Okay, so times 1 over n, then the integral of cosine u du from 0 to pi. So 1 over n pi. Then again, the integral of cosine is sine. So we can rewrite this as sine. Okay, so u natin is nx evaluated from 0 to pi. So 1 over n pi. So upper limit minus lower limit. This will give us what? n pi minus sine of 0. Okay, so sine of 0 is, of course, what? 0 to, no? So we're left here with 1 over n pi. Okay, then sine n pi na lang. So, ito magiging result. So, 0 siya kasi again, if you try to evaluate yung sine ng n pi, so if n is equals to 1, we're evaluating sine ng pi which is 0. If n is equals to 2, we're evaluating sine ng 2 pi which is also equals to 0. So always 0 to, no? So of course sine 0 is 0 then. So of course 0 minus 0 is 0 times 1 over n pi. This will give us 0 value. Okay, so last coefficient, b sub n. So we have this formula. So this will give us 1 over pi, then times the integral of negative pi to 0. So our function is defined as 0 times sine nx. So this will give us 0 times dx plus 1 over pi, then times the integral of sine x dx from 0 to pi na lang, no? Kasi our function is defined as 1 from 0 to pi. So if we try to evaluate this, this will give us this one. Oh. So let's try. So 1 over pi, 0 to pi. So it should be sine nx, no? So nx dx. So again, u is nx, du is n dx. So ang dx natin is 1 over n du. So 1 over pi sine ng u, 1 over n du. So again, we can factor out 1 over n, then times 1 over pi is 1 over n pi, no? So sine ng u du. So again, the integral of sine u is negative cosine u. So this give us negative 1 over n pi, okay? Then times cosine ng u. So ang u natin is nx evaluated from 0 to pi. So upper limit minus the lower limit. This will give us what? Cosine ng 0 to, no? Okay. So what's cosine ng 0? This is always equal to, this is always equal to 1, no? Okay. And cosine n pi, we have two possible values, either negative 1 or 1, no? Kasi if n is 1, we're evaluating cosine of pi, which is negative 1. If n is equals to 2, the value of cosine 2 pi is uh, positive 1. So if we try to simplify the value of b sub n, this will give us negative 1 over n pi, then times cosine n pi minus cosine 0, or just minus 1. No? So if we try to substitute, okay, or let's say substitute a certain values of n, so we can generate this two possible values of p sub n, so either 0 or 2 over n pi. So based on the result, so if n is equals to 1, okay, so we have this value for b sub n. So negative 1 over n pi cosine ng uh, pi is negative 1. So negative 1 minus 1, this will give us negative 2. So positive 2 over n pi, no? If n is equals to 2, negative 1 over n pi, cosine ng 2 pi is 1. Okay? Then this is always minus 1, no? So of course, 1 minus 1 is 0. 0 times negative 1 over n pi is 0. So if n is equals to 3, negative 1 over n pi, cosine ng 3 pi is negative 1. Okay, so then minus, of course, minus cosine 0 is minus 1. So this is, so of course, if n is equals to 1, this is 2 over pi na lang, no? Then negative 2 or 2 over n pi. So if n is equals to 3, this will give us 2 thirds pi, no? So if n is equals to 4, so of course n2, so 4 pi, cosine ng 4 pi is what? 1. Then minus 1, this will give us 0. So as you can see, we have the pattern. If n is odd number, 1, 3, 5, and so on, we have a fixed value of 2 over n pi. Okay. Now, if n is even, 2, 4, 6, 8, so we have a fixed value of the b sub n as 0. Then the Fourier series of f can be therefore expressed as in this form. No? So initially we have the value of a sub naught, turns out to be 1 half. Okay. Then a sub 1 is, or a sub n turns out to be equal to 0. Okay. Then for b sub n, Okay, so we have this condition if n is odd, starting with the first value of n, which is 1, which is an odd number. So we have a fixed uh, value of 2 over pi for the value of p sub 1. Okay, so 2 over pi, then sine x, okay, then plus. So if n is equals to 2, 2 is considered as an even number. So we expect that the value of the b sub 2 is 0. Okay, that's why we have here 0, then sine 2x, then plus. The next value of n is, of course, 3. 3 is considered as an odd number. So 2 over 3 pi as the value of b sub 3. Okay, then sine 3x and so on. Okay, and of course, if the a sub n value is 0, that means to say that a sub 1, a sub 2, a sub 3, a sub 4, and so on are all equal to 0. So of course, we can further simplify this as in this form. We can eliminate the following terms. No, it contains a 0 uh, numerical coefficient. So 1 half, okay, plus 2 over pi sine x plus 2 over 3 pi sine 3x plus 2 over 5 pi sine 5 pi and so on. So since odd integers can be written as in this form, n is equals to 2k minus 1, where k here is an integer, we can rewrite the given Fourier series using the sigma notation as in this form. So 1 half, so 1 half here represent the value of a sub naught plus the summation of 2 over odd number times pi, then times sine of odd number times x. Okay, where k here will run from 1 to infinity. Since we have here a pattern of 2 over odd number times pi sine odd number times x. Okay, so this one will be discussed next meeting, no, in Fourier convergence theorem. So thank you for listening.